this video, we're going to find the eigenvalues and eigenvectors of this 3 by 3 matrix. The first row is 0, 1, 1. The second row is 1, 0, 1. The third row is 1, 1, 0. So the first step is to find the eigenvalues, and we do that using the characteristic polynomial. The characteristic polynomial is the determinant of a minus lambda I. So I take this matrix and subtract lambda on the main diagonal. That gives me this matrix. The characteristic polynomial of A is the determinant of this matrix. So I need to do a cofactor expansion to calculate the determinant. Now there are a number of ways that can make the process go a bit faster if you have to calculate the determinant of a matrix, because you can use elementary row operations. And the determinant plays nicely with elementary row operations. But when you have lambdas, it's usually not a good idea to do too many elementary row operations because lambda might be 0. And so you run into this issue if you try to, say, divide by lambda. So for instance, dividing the first row by lambda is only possible if you assume that lambda is not 0. So in general, for finding the characteristic polynomial, it's actually usually better to just do a cofactor expansion. So I'm going to use cofactor expansion. It doesn't look like any row or column is particularly easy to work with because there are no zeros. So I'm just going to use the first row. So when you do cofactor expansion along the first row, you get negative lambda and then times the determinant of this submatrix. So you get lambda squared minus 1. And then you have minus. Remember, it alternates plus minus plus. So I have minus 1 times, and then you take the determinant of the submatrix. So you get negative lambda minus 1. And then plus 1 times the determinant of the submatrix. So you get 1 plus lambda. And now we are going to have to factor this. So let's distribute this all out. Get negative lambda cubed plus lambda plus 1 plus 1 plus lambda. And that is negative lambda cubed plus 3 lambda plus 2. Now we need to find the roots of this, because the roots of the characteristic polynomial are the eigenvalues. So we set this characteristic polynomial equal to 0. And just to make it a little easier, I'm going to divide everything by negative 1 so that the leading coefficient is positive. So now I have to factor, or find the roots anyway, of lambda cubed minus 3 lambda minus 2 equals 0. So this is a cubic polynomial. And in general, what you want to do is you want to find a factor. You want to find a root of this cubic polynomial, and then you can factor out lambda minus that root. And then you get this quadratic. So one way is to just guess values of lambda and through trial and error find one that works. But notice that this is a polynomial with integer coefficients. And we can use the rational roots theorem to narrow down the possible roots. So the rational roots theorem says that if you have a polynomial, so it's an x to the n plus an minus 1 times x to the n minus 1 plus dot 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 plus a1x plus 0, a1x plus a0. So if this is a polynomial with integer coefficients, so in other words, the ai's are all integers, then any rational root, so rational root meaning a fraction, has the form x equals p over q. Well, that just says it's a rational number, but p and q have to satisfy a few properties. P has to be a factor of a naught, and q has to be a factor of an. It's not a very hard theorem to prove. Basically what you do is you plug in x equals p over q into your polynomial. So if p over q is a root, you get 0. And then basically you multiply everything out. And when you look at the equation you get, you can see that p has to be a factor of a0 and q has to be a factor of a sub n. Okay. So I'm not actually explaining the details, but basically I'm just trying to say that it's not a very deep theorem that requires lots and lots of difficult math to prove. Okay, so let's just take this for granted, okay? Or you could try to prove it by yourself. So let's apply this rational roots theorem to the polynomial x cubed minus 3x minus 2. So your a, let's see, we have a cubic polynomial, so we have an a3 equals 1, and then an a0 is a negative 2, right? So by the rational roots theorem, which I'll abbreviate to RRT, the only possible rational roots of lambda cubed minus 3 lambda minus 2 are, so p has to be a factor of a0, so that's negative 2. Q has to be a factor of an, which is 1. And when we mean factor, we include positive and negative factors. So the possibilities for p are 1, 2, negative 1, and negative 2. The only possibilities for q are 1 and negative 1. So then when you take all the possible p over q's, you see that the only possible values you get are 1, negative 1, 2, and negative 2. Now I'm not saying that every polynomial with integer or rational coefficients has to have a rational root. That's not true. But if you have a polynomial of odd degree, it turns out it is true. Okay. If you think about it, I'll just let you think about why for an odd degree polynomial, with integer or rational coefficients, you have to have an integer or rational root. But if you have like a quadratic, if you have x squared plus 2, right, that has no real roots. So, but here we have a cubic polynomial, and in general, if you have a polynomial that you're trying to find the roots of, you can narrow down the possibilities of the rational roots by using the rational roots theorem. Okay. So anyway, going back to this example, we can just test the possible rational roots and see if they work. So for instance, there's no point in testing 3 or negative 3 or 4 or negative 4. Like we know by the rational roots theorem that those are not going to be roots. I mean, there's only 4 possible rational roots. And so you test them. So you test 1. And if you test 1, you get 1 minus 3 minus 2. That doesn't make 0, so that doesn't work. If you test negative 1, you get negative 1 plus 3 minus 2, which works because you get 0. So I know that lambda plus 1 is a factor, right? So negative 1 is a root. So that means that lambda plus 1 is a factor. And now to figure out how to factor, I can use long division. So I have lambda cubed plus 0 lambda squared minus 3 lambda minus 2. When you do long division, you want to make sure that you have a space for each of the powers of lambda. So, okay, lambda plus 1 is a factor, and now we just do long division. So lambda squared, and then you multiply. Let's get lambda cubed plus lambda squared. You subtract, so you get negative lambda squared minus 3 lambda. Then you continue, you get minus lambda squared minus lambda. Subtract, and you get negative 3 plus lambda is negative 2 lambda. Bring down to minus 2, and then negative 2. So negative 2 lambda minus 2. Subtracted, you get 0. So that shows that the characteristic polynomial factors as lambda plus 1 times lambda squared minus lambda minus 2. And now we can easily factor this quadratic because that's going to factor as lambda minus 2 times lambda plus 1. So we see that we get lambda plus 1 squared times lambda minus 2. So the characteristic polynomial was negative this. So if you want the characteristic polynomial, you multiply this by negative 1. But we're trying to find the roots of this. So we know, now that we've factored this polynomial, we see that the eigenvalues are negative 1 and 2, right? Because they're the roots of that polynomial. Okay, so those are the eigenvalues. Now we need to find the eigenvectors. So that basically amounts to finding the eigenspace, right? The space of eigenvectors for each of the eigenvalues. So let's look at the eigenvalue negative 1. We find, so for negative 1, let's just call this lambda 1. For this one, we need to find a minus negative 1I, right? So this is going to be 1, 1, 1, 1, 1, 1, 1, 1, 1. Because remember why we're doing this. Because if v is an eigenvector with eigenvalue lambda, then AV equals lambda v. That's the same as a minus lambda I times v equals 0. So I'm solving this homogeneous system, a minus lambda I times v equals 0. So we need to find a minus lambda I first, and that's what I'm doing. So now we're solving the homogeneous system. And if you want, you can write the augmented matrix, right? So this is the coefficient matrix of my system. When you're solving a homogeneous system, your augmented column, okay, it's just going to be zeros, right? So when you do the row reduction operation, those zeros on that rightmost column are still going to be 0. So that's why I tend to not write that column of zeros, because I know that it's just going to be zeros. But if you're beginning and you're just getting used to this, it might be a good idea to write a column of zeros and then work with the augmented matrix. But I'm just going to work with the coefficient matrix. So this is going to row reduce to 1, 1, 1, 0, 0, 0, 0, 0, 0, right? So this is my coefficient matrix in reduced row echelon form. And now when I write down the equation, I get x, this first row tells me x plus y plus z equals 0. So I know that I need to solve this equation. I need to find a basis for the vectors that satisfy this equation. And I know that I can just, this is a rank 1 matrix, so the nullity is 2-dimensional, so I just need to find 2 independent eigenvectors. And you could, set y and z equal to like s and t and then solve for x and then get your 2 vectors that way. But you can also just, by hand, just come up with 2 solutions to x plus y plus z equals 0 that are independent. So just pick v1 to be 1, negative 1, 0. And v2 to be 0, 1, negative 1. And of course, these are not the only possible choices. You could pick 7, 2, negative 9, and 5, 1, negative 6. I mean, those are 2 solutions that, so they're in the null space of this matrix, and they're independent, so that would work. But, might as well just pick an easy choice involving 1s and 0s. So that's my choice of v1 and v2. So the eigenspace with eigenvalue negative 1 is all vectors of the form c1 v1 plus c2 v2, where c1 and c2 are real numbers. Okay, so now let's look at the 2 eigenspace. So that's when lambda is 2, so my second eigenvalue. Now I want a minus lambda I, so I get a minus 2i. This time I'm going to get negative 2, 1, 1, 1, negative 2, 1, 1, 1, negative 2. And I'm going to skip the row reduction steps. There are quite a few steps, but when you calculate the reduced row echelon form, you end up getting this matrix. Okay, the first row is 1, 0, negative 1. Second row is 0, 1, negative 1. Third row is 0, 0, 0. And so now the equations we get are just x minus z equals 0, so that's x equals z. Second equation is y minus z equals 0, that's y equals z. So again, it's easy to just find a vector. Now this is a rank 2 matrix, so the nullity, the dimension of the null space is 1, right? So I just need one independent, well, I just need one non-zero vector in the null space. That's going to span the null space. So let's pick V3. Again, we just need one vector where x is z and y is z. That's not the 0 vector. So why not just pick 1, 1, 1? That's perfectly fine. Now you could pick 7, 7, 7, or pi, 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 or the square root of the 2, square root of the 2, square root of the 2. That's perfectly fine for V3 because the eigenspace is just a span, and they have the same span. So the 2 eigenspace is all multiples, all scalar multiples of V3. So it's the set of vectors of the form C3, V3, where C3 is a real number. Or, you can just write C3, V3. I think most people will understand what that means. That means C3 can be any real number. So that's the 2 eigenspace, that's the -1 eigenspace. And so what's going on is the -1 eigenspace is this plane. So basically there's this plane that's spanned by V1 and V2. And that plane, it's the vectors of the form x plus y plus z equals 0, right? That plane that passes through the origin is, what A does to it is it multiplies all of the vectors by -1. So it basically ends up flipping the plane. It flips all the vectors over, right? Because when you multiply a vector by -1, it just flips the direction. And then what it does to this line spanned by 1, 1, 1 is this matrix stretches that line by a factor of 2. So the line and the plane are not, are they orthogonal? No, right? If you take V3, it's not orthogonal to V1 and V2. So you have this plane and then you have this line that are not orthogonal to each other, but A is flipping the plane across and then A is stretching that line. Okay, so that's a 3x3 example of finding the eigenvalues and eigenvalues and eigenvectors. And this question didn't ask for diagonalization, but let's say you wanted to diagonalize the matrix. So let's just do something a bit extra. So your A can be written in the form PDP inverse, where P is the matrix with columns V1, V2, and V3, right? So 1, -1, 0. 0, 1, -1. V3 is 1, 1, 1. So this is this matrix times, and then D. So V1 and V2 had eigenvalue -1. So I have -1 on the diagonal, and then I have a 2, and then the inverse of this matrix P. So that would be a diagonalization of the matrix A. Okay, so I've written it in the form PDP inverse.